Right, so welcome everybody to the first NCG&T seminar of 2025. We're pleased to have David Jekel from the University of Copenhagen, who will talk to us about free optimal transport on the trace state space.
Yeah, thank you very much for this invitation. And yeah, thank you for the pre-seminar presentation. I will recall some of the things from there, but I'm glad that we had this background. So here's the outline of things that I plan to get to. So firstly, talking about random matrices and free probability for the kind of context and motivation of this topic. And then I'll talk about results of about some kind of smooth change of coordinates in this free probability setting. And after that, I'll get to the Wasserstein distance and various properties of this Wasserstein space. And then I'll get to the analog of Monch-Kantorovich duality, which is a fundamental result in optimal transport theory we are adapting to the non-commutative setting. And this was also mentioned in the pre-seminar. And then finally, if there's sufficient time and interest, I'll talk a little bit about like how continuous model theory can be combined with this and how this tells you, and that then in this case, this Wasserstein distance will give you information about the distance between automorphism orbits in operator algebras. And I just added this part because I was talking with a couple people yesterday who know a little bit about model theory, and I thought you may appreciate this. And by the way, we're planning to discuss related topics tomorrow, so if anyone else wants to hear more about this part, you can meet tomorrow as well. I'll be here tomorrow. I'll leave on Thursday morning, so anytime tomorrow is good. Okay, so a bit about random matrix theory, and this was also covered in the pre-seminar a little bit, right? And we're trying to develop optimal transport theory in this context, where you're trying to study the large n behavior of n by n random matrices. And what do you mean by random matrices? It just means a random variable that takes values in the matrix algebra. And we'll also focus on the self-adjoint case. And you can consider the self-adjoint matrices as a real vector space of dimension n squared. And the prototypical example is the so-called Gaussian unitary ensemble. The reason it's called this is because it's a Gaussian random matrix. The entries are jointly Gaussian, and they're independent up to symmetry. And there's a certain normalization on it. And it's called the Gaussian unitary ensemble on account of the distribution being invariant under conjugation by unitaries. And Wigner's semicircle law is a famous result. Wigner was studying this in hopes of having similar behavior to the energy levels of atoms. And he showed that in the large n limit, the distribution of eigenvalues converges to a semicircular density from -2 to 2. Now, what I'm interested in is not just a single matrix, but several random matrices, which, as you'll hopefully see, is like qualitatively much harder than the single matrix case. And the reason is because in the single matrix case, you can say, well, okay, I just want to look at the distribution of eigenvalues, right? And then maybe I want to look at the operator norm and some other things. When you have several matrices, and you want to discuss what is the joint distribution, you cannot reduce it to a classical object like a probability measure, because even like if you wanted to study the moments of it, you'd want to study joint moments. And here you would take some monomial, right, like some product of xi1 to xik, and because they're not commutative, then these are not commutative polynomials, right? You're looking at like the non-commutative polynomial algebra. And and somehow the distribution should be some kind of state or positive functional on that, but that's not a commutative space, right? So these states will not correspond to probability measures, as in the classical case. It's just a new object that you have to study. And in many situations in random matrix theory, you study certain models and try to prove that as n goes to infinity, the limit of the expected value of this trace would exist. And furthermore, you might also want to prove that the limit of the trace exists almost surely. Right? And this often happens because when you have these high-dimensional random matrix models, there's a phenomenon of concentration of measure, which means that these kind of macroscopic functions are going to be close to their expectation with high probability, and so you would expect some kind of deterministic limit. So in this setting, there is an analog of independence, as discussed in the pre-seminar, and it's called free independence. And what does this mean? Well, so the statement is shown by Voiculescu that if you take several random matrices and they're independent of each other, and their distributions are sufficiently symmetric, i.e. they're invariant under unitary conjugation, then in the large N limit, they become freely independent. And there's also many generalizations of this theorem. For instance, like if you have permutation invariant random matrices, right, or various things, right, or Wigner matrices, which are just matrices with IID entries, but they're not necessarily invariant under unitary conjugation. Right? So anyway, in these situations, you often get free independence. And as an example, you could consider the unitary case. And it's easy to state this because in this case, the limiting object can be described by the free group itself. Right? So if you take the Haar unitaries and you take some word in the Haar unitaries and their adjoints, then the trace of this will converge almost surely to 0 unless the word could already be reduced to the identity by cancellations. Right? So they model somehow the free group. And more generally, this condition of free independence, which was explained in the pre-seminar, it corresponds to, in the large N limit, the traces behave as if you're in the reduced free product of some C-star algebras or von Neumann algebras. Okay, so in order to describe the limiting objects for these random matrices, like I said, you can't use a classical measure to do it. You have to use these non-commutative objects, which you can use tracial von Neumann algebras, or if you like, just a C-star algebra with a trace, just depending on whether you feel like using a C-star algebra or a von Neumann algebra. And these are nice objects because they kind of, the properties that you have for the random matrix setup are mirrored in the tracial von Neumann algebras, right? So some of the properties that you have, well, you have random elements of the matrix algebra, and in the matrix algebra, if you have random variables there, you can add and multiply them, but it's a non-commutative multiplication. And then there's an analog of expectation. I mean, besides just taking the expectation of the vector value thing, really what you want to think about in this case is the expected expectation of the trace of some function of. Yeah, and if you think of them as analogous to complex random variables, somehow the analog of complex conjugation should be taking the adjoint, right? Because, for instance, if you had a normal operator and you diagonalized it, right, and like taking the complex conjugate of the eigenvalues would correspond to taking the adjoint. Okay, so this leads to the definition of non-commutative probability space. And these are the axioms that you want to have. You have some star algebra, which means it has addition, multiplication, and a star operation that has the same properties as adjoint. And then you want to study tracial state on it. So the tracial state, well, it's a linear functional. It maps 1 to 1. It satisfies trace of AB is trace of BA. That's the traciality part. And then you have positivity. Like trace of A star A is non-negative. And the last part, the last condition would be called faithfulness, right? That if the trace of A star A equals 0, then A has to equal 0. And like I said, you can have this, just as an algebra, right? You can also assume that it's a C-star algebra if you want, or you could also assume that it's a von Neumann algebra. Like all of these are valid settings to consider. And I think in most of the slides I maybe refer to von Neumann algebras because this is where I come from here, but it's kind of the thing that matters is like what are the random variables and what's their joint distribution. And you can define this without necessarily having a von Neumann algebra to solve. Okay, so in the intuition, like I said, is these are elements of A are something like random variables, but they just don't commute when you multiply them, right? And so, but you can try to pursue and treat it as if it's like a probability space, and these are random variables, just without commutativity. And yeah.
Obvious at this point why you focus on tracial states as opposed to
Yeah, so it is a valid question to study states that are not tracial, right? No, and then maybe there's a little bit more that you have to think about, because if you really want to do this in von Neumann algebra setting, you have to think about the modular theory to make everything work correctly. And for instance, I mean, if you just think about an arbitrary state on a C-star algebra, right, there are many states that you'll be interested in that are not faithful, right? Or you can have a representation that's faithful, but the state itself is not faithful. I mean, it doesn't satisfy that phi of A star A equals 0 implies A equals 0. And somehow you can't avoid those things in a non-commutative setting unless you kind of impose some condition of faithfulness and think about the modular theory. Yeah, and the other reason is if I'm studying a large n limit of matrices, then I only need to think about the tracial case in a sense, because I'm studying the limits of tracial objects. Yes. Okay, so going back to the analog of probability distributions, right? You can't capture it by a classical measure. If you wanted to use polynomial test functions, they have to be non-commutative polynomials, right? And so this leads to the definition of non-commutative laws, which I think was also talked about in the pre-seminar. And I'll tell you a formal definition in a second, but I mean, maybe this is like a definition which is kind of practical in the sense that if you tell it to someone who doesn't know operator algebras, then there won't be undefined terms in here, right? And the idea is, well, the non-commutative law should capture the non-commutative moments where you take the trace of any like monomials in the x's, and convergence in non-commutative law, or in the weak-star topology, should mean that each of these moments converge. And here, one of the nice things about the random matrix setting is that often these things, as n goes to infinity, are asymptotically bounded in operator limit. So unlike a classical probability where you need to study the Gaussian distribution and stuff, so you shouldn't really assume your random variables are bounded. Like in a non-commutative setting, often they are bounded anyway. And if they're bounded, then I can just use polynomial test functions, right? Because polynomials are dense in the continuous functions on a compact set. So then this sort of makes sense. But then here's the formal definition. You have the algebra of non-commutative polynomials. It's an algebraic object. It also becomes a star algebra where you have the star operation that makes them self-adjoint. And then the non-commutative laws are linear functionals satisfying certain properties, right? Which are basically the same as we had for tracial von Neumann algebras. They're unital and they're tracial and they're positive, but I won't assume that it's faithful. And then we also have this other condition, which is some kind of bound, that if you apply it to some monomial, then it's at most like something to the power of that degree. And the reason that we have that condition is because it will guarantee that the things that this actually corresponds to some bounded operators. And then again, like I said, there's a weak star topology. So just if you consider these as linear functionals on the polynomial algebra, then it makes sense to define weak star topology. By the way, weak star topology makes sense regardless of whether the original vector space was a Banach space or not, right? You don't really care what the topology, if there was any topology on the original space, you can still define weak star topology on the dual. Right, and the fact is that anything satisfying those properties, this exponential boundedness, will actually come from some operators in some tracial von Neumann algebra. Or even a C-star algebra, if you like. Right, so if you have a C-star algebra and if you have some self-adjoint tuple, then you obtain this linear functional by just mapping each polynomial to the trace of its evaluation on X. And then conversely, if you have something like this, then you can construct such a C-star algebra. And this is basically because of the GNS construction, but there's a little bit of extra argument because because this isn't a C-star algebra, right? So you have to somehow use this exponential boundedness and to argue that the multiplications actually define bounded operators, which you can see in this textbook of Anderson, Guillenet, and Zeytouni. And so the upshot of this is, if you're a C-star algebraist, like, what is this space of non-commutative laws? This is nothing but the trace space of some universal free product of continuous functions on some interval. Right, so if you want to think of it this way, no, you can think of it like this. And of course, because this is a huge C-star algebra, like, there are tons and tons of traces on here, right? So it's a very not simple, not nuclear, very huge.
Paulson simplex, this
Yeah, it's a Paulson simplex. Yeah. Okay. Well, I mean, I'm not going to try to talk about that now, but we can talk about this later. Why it's a Paulson simplex, etc. Okay. Right. And the other way that you could think of this is helpful is that the non-commutative law is somehow capturing an equivalence class of having a C-star algebra and having a choice of generators. Right, so you could consider isomorphism that maps the one thing to the other and maps the corresponding generators to the other generators. Right, and then this would be in bijection with the non-commutative laws. Okay, so now I'm going to try to discuss a smooth change of coordinates for this setup, right? And the goal of this is the following. Well, say that we have two different C-star algebras or von Neumann algebras that are generated by these things, and say that, like, we're given these non-commutative laws, like somehow like some kind of non-commutative moments or probability distribution. And then how can we figure out whether the operator algebras are isomorphic or not? Right, here here the isomorphism doesn't necessarily map the one generating set to the other generating set. Right, so how can you tell when they're isomorphic? And in the setting that I care about for random matrices, you have maybe some kind of analog of smooth density, or you're coming from some nice random matrix model, and you want to be able to have an analog of some kind of change of coordinates, which could be, if you want, homeomorphism or diffeomorphism or measure preserving transformation, depending on what particular result you're aiming at. Okay, and in this case, you don't actually have a smooth analog of density for the random matrix setting, because again, these are not, the non-commutative law isn't a classical probability measure. And also, this is not the same as the quantum setting where you would have like an operator of trace 1 to act as an analog of density, right? This is a different setting. And it turns out that what you might want to look at is something like the log of the density. And this will be somehow a scalar valued function which takes as inputs these non-commutative variables. So what do I mean by this more precisely? Well, we often study random matrix models that come from some potential. If you want, you can think of this as like some kind of statistical mechanics type construction, and the potential V is like describing the interaction between the several different matrices and also the interaction between the different entries of each matrix. Right? And so this V is also going to play the role of like the log of the density. And because we have n squared up here, then you can't say that the density itself would have a limit. But if you take the log of the density with the right normalization, then it makes sense. And the V that we choose would be some function which makes sense kind of in a uniform way on all the different sizes of matrices. For instance, you could take V to be the trace of some non-commutative polynomial. And more generally, there's some kind of analog of smooth functions in non-commutative variables. In fact, maybe there's like several possible definitions, but one of them is in this paper here, which is my paper with Wu-Chen Li and Dimesh Sliaktenko. And it's basically somehow you take traces of different non-commutative polynomials, and then you allow yourself to multiply together different traces, and create this space of trace polynomials. And then you take a completion of this with respect to a certain norm, where you would look at the maximum value of the function on operator norm balls, and also like look at derivatives of it. And so then you can define some kind of smooth functions, which I'm not going to go into detail in, but again, if you're kind of interested in this, then you can ask me tomorrow if you want. And okay, so we have some kind of matrix models like this. And then in a lot of the theorems that I give, we'll want to assume that the V is convex. And in fact, you'd want it to be strongly convex, which means that even after subtracting a multiple of the norm of x squared, it's still convex. Right? Or another way you can think of it is like in the distributional sense, the Hessian of V is bounded above and below by some positive constant. So this would be a strongly convex and semi-concave. Okay, so there are a lot of examples that satisfy this. Maybe as operator algebraists or other people, perhaps you do not necessarily care about this particular random matrix model. Okay, but a lot of people have thought about Q Gaussians. Q Gaussians are, you define some non-commutative random variables. The moments are given by some kind of combinatorial formula, and for the parameter Q, as you move it between -1 and 1, it kind of interpolates between different scenarios, right? So when Q equals 0, it gives you the free case. When Q equals 1, it gives you the classical Gaussians. And when Q equals -1, it gives you the fermionic case where you may have some kind of, well, I won't go into that, okay? But the point of this is that if the Q is small enough, right? If Q is basically like smaller than a constant times the square root of 1 over d, where d is the number of variables, then it will be true that these have a random matrix model in this form. And by the way, I mean, there's a lot of recent work on Q Gaussians, and Miyagawa and Speicher gave another formula for what would be the gradient of V. And so it makes it even easier to see this than the original proofs. Right? And another example that's very where you can apply the results that I will say later is if you start out with the freely independent semicirculars, right? And these semicirculars, they generate the von Neumann algebra that's same as the von Neumann algebra of the free group. And say you take these generators and then you decide that you're going to perturb them. So take the S plus epsilon times f of s, where f is a tuple of non-commutative polynomials, or more generally, some kind of smooth functions. And then you can argue that this new random variable will have random matrix models of this form for some v. And the reason for this is that basically, it just comes from kind of the change of variables formula for push forward of some density. So if you take some density and then you push forward by some diffeomorphism, right, you use the change of variables formula to compute the density by like taking the Jacobian and taking the composition of the function. And if you work all this out, right, if you use that, if you took like just the quadratic function for v, that gives you the semicirculars, and then if you took your function f and then applied this push forward formula, then you get out some other function. And if the function is close enough to the identity, then the new density that you get out will be still convex. So this is another example which fits into this framework. And more generally, this change of variables works whenever you have something that you start with this nice smooth log density, you can do change of variables to that and obtain other things. Okay. Right, so these are examples of things that fit in this framework. And now if you have this setup, okay, and if this V satisfies these convexity assumptions, then there will be a limiting law as n goes to infinity. So the non-commutative law of the x1 through xd will converge almost surely to some limit. And this limit, and there's also ways to describe and construct this limit using Dyson-Schwinger equations, and basically like the free version of integration by parts, and also there's various ways to write formulas for this. Right, and so we have random matrix models. We know they converge to a limit, and so then now we can talk about, well, what happens to the change of coordinates for this? Right? Can you take the random matrix model that you're given? If you just handed a random matrix model and then you say, I want to transform this into something canonical, like the free semicircular family, can you do that? And the answer is yes. If this V satisfies these convexity assumptions, then this is fine. So if you take x, which is this limit, and if you take z, which is the free semicircular family, then there will exist some sort of non-commutative diffeomorphism, which can be done in some cases. If you want, you can do it in a power series setting, or you can do it in the tracial smooth function setting. All right, but there exists some transformation that transforms this into the semicirculars. And in particular, what this means is the von Neumann algebra generated by X is the same as the free group von Neumann algebra. And as if you're in classical probability, then you'd be like, well, of course. I mean, why is this good? Because, of course, like in classical probability, any two diffuse probability spaces are the same. If they're separable and if they're diffuse, then they will be the same. So, and if you took like 3 Gaussian random variables and 2 Gaussian random variables, you get the same thing in classical probability. But in the non-commutative setting, this is very much not obvious. Like, okay, we don't know whether the free group on 3 generators or on 2 generators give you isomorphic von Neumann algebras or not. And furthermore, it wasn't obvious whether the random matrix models from these convex V would give you the same von Neumann algebra in the limit as the free group von Neumann algebra. You need some kind of construction to obtain this. And this is what this result accomplishes. And I suppose I should also mention the result of Figali and Guillenet. They used this such transport techniques for a bit of a different purpose, and that was to study. Well, they studied again like perturbations of the say Gaussian random matrices, and they used the transport function to analyze the local statistics of eigenvalues, like the spacings between them and like the behavior of the edge and all those things. So there are other applications for transport as well. Okay, so where I came in this story was in my PhD thesis and in this paper cited here, I gave a triangular version of the smooth transport construction. And actually, there were various things. I mean, I took a bit of a different approach to doing it. So I studied more closely the finite dimensional transport functions at each level and showed that they would have a nice limiting behavior as n goes to infinity. But I mean, the main interesting thing about this, as far as von Neumann algebras are concerned, is that you can get the function in the previous theorem to become triangular, meaning that the jth output only depends on the first j inputs. And what that would mean in terms of the operator algebra is that not only do you have an isomorphism of those von Neumann algebras, but you choose the isomorphism in such a way that the thing generated by the first j elements, the first j generators, is mapped to the thing generated by the other first j generators. Right? So in particular, like the von Neumann algebra of x1 is mapped to the von Neumann algebra of y1. And thus, just as like you get the non-obvious statement that the von Neumann algebra is isomorphic to free group von Neumann algebra, you also get a statement about the subalgebras generated by the subsets of the generators. And by the way, I mean, this also works for the C-star algebras because of if the function is nice enough, then you'll get isomorphism of the C-star algebras as well. So not only of the von Neumann algebras. So then, like I said, right, the von Neumann algebra of the first generator and the first generator in the other set will be the same up to isomorphism of the inclusions in a larger algebra. So, for instance, that means that the first one here being maximal amenable thanks to Popa, right, or other properties like this, they also apply to the other one because you can transform it to the other one. And I think, Popa has recently been thinking a lot about whether if you take a maximal amenable subalgebra of the free group von Neumann algebra, whether it's freely complemented, meaning like whether the entire algebra can be expressed as a free product of that thing with something else, right? So this is showing like, okay, if you have like smooth perturbations of one of the generators, then it gives you something that's freely complemented. Right? The whole thing can be decomposed as a free product because you can transform it to the case of the freely independent semicirculars. Yeah. Yep. Okay. So that was like the first bit about smooth change of coordinates, right? And you already see that this has some nice applications to von Neumann algebras and C-star algebras because it wasn't clear before this, like whether they're isomorphic or for the triangular case, like whether these subalgebras behave in the same way as the freely independent case, and it turns out that they are. If the V that you start with is nice enough, and if the V is not convex, then things don't necessarily work out like this. For instance, in the Q Gaussian case, you can argue by examining the proof that Caspers gave that Q Gaussian with infinitely many generators is not isomorphic to free group polynomial algebra. And if you examine this proof, it will also tell you that if you look at the subalgebra generated by some subset of the generators, it will not be freely complemented. But this only works for more than two. So I don't know about a single generator in this case, but you can deduce that these triangular transport results are not true in all settings, right? It does require something special here. Okay, so now to talk a bit about Wasserstein distance. Okay, so the smooth change of coordinates results, right? Maybe I didn't mention anything about optimal transport here necessarily. It was just about having some transport, and maybe you care more about whether the transport is smooth than whether it's optimal and gives you the closest distance to the original thing. Okay, but the technique that UNA and Sliaktenko used for this, they did construct maps that sort of should be optimal because they were obtained as somehow the gradient of a convex function. And so it was very tightly related to trying to study the Wasserstein distance, right? So, and so I'm going to talk about the Wasserstein distance defined by Bion and Voiculescu, and also the properties of this a bit. So, firstly, what is transport of measure? That's basically transforming one measure into the other by taking the push forward by some measurable function, right? And perhaps even a smooth function if you want. And there are many applications of optimal transport in terms of applied math and optimization and everything, because you're trying to figure out the most efficient way to transfer some kind of objects that are in one distribution into some other distribution. Maybe you have pieces of bread that have been baked at different locations, right? And then they have to be delivered to the people that will sell the bread. So and you have to do this in the most efficient way possible. You don't want to be traveling lots of extra distance, right? So then you can try to study this problem, which was studied by Monge, how can you minimize this kind of squared distance? And the optimal value of the distance is the so-called Wasserstein distance, right? And in the smooth case, you can always realize this by some f, but then there might be a case where the mu and nu are not necessarily smooth measures, and so then you wouldn't necessarily expect that you're able to apply a function to it. Because, for instance, in the case with atoms that was discussed in the pre-seminar, right, if the sizes of the atoms don't match, then maybe you can't even find a function that takes the one thing to the other. Right? But so there's a relaxed version of the problem, and you just think of it as, well, I consider not necessarily a function, but I just consider two random variables on the same probability space, which have the specified distributions mu and nu, and then I try to make the x and y as close as possible together. And so this is the general definition of the Wasserstein distance. And when I say coupling, the coupling just refers to some kind of realization of x of the two distributions by random variables on a common probability space. Right? So that is the coupling. Now, we want to generalize this to the non-commutative setting. And Bion and Voiculescu did this a long time ago in 2001, that you can define the Wasserstein distance in an analogous way. You consider non-commutative laws, and you consider couplings of them, which is just any tuples x and y in the same non-commutative probability space, which have the given distributions mu and nu. And so then you try to minimize the distance between them. And I should also remark here that there have been many attempts to define non-commutative analogs of Wasserstein distance. And some of them occur from the quantum setting, where again, what you're studying is your state is given by some density operator and it's some positive operator of trace 1, and you study like the evolution of the systems by some unitary conjugation, as in quantum mechanics, and then you would want to find some kind of Wasserstein distance in that setting. And maybe it wasn't clear like how this would actually relate to the free version, but recent work of Duvenhage, which is actually, I guess, maybe 2 or 3 years ago now, and the way that he set up this quantum Wasserstein distance is actually pretty close to the free probability case. And in that case, it's with like non-tracial states, right? So you bring in the modular automorphism group into it, and then the definition of couplings isn't just embeddings of the algebra into a larger algebra or realizations in some larger algebra as here, but you actually use bimodules instead. But it's like modulo of those two changes, it basically ends up being the same thing. So there is a lot of work to do to try to figure out the connections between these things and build a coherent theory that bridges the two. So that's something I'm thinking about a lot recently, which you're free to talk to me about or think about as well. Right. So in the Bianen-Voiculescu distance, it should be noted that you take the infimum over all possible couplings, and that includes allowing the ambient non-commutative probability space to vary. Right. So because in contrast to classical probability, there's tons of different von Neumann algebras that are not isomorphic to each other. Right? There are even like uncountably many that cannot embed into each other, which was shown by Ozawa. And so it will make a difference, if you fix one non-commutative probability space and try to find the infimum over couplings in there, you get a different answer than if you allow the ambient space to vary. Right? So it's important to try to figure out what is the correct ambient space to use, and here in this definition, it's allowed to be anything. So, and the fact of having uncountably many von Neumann algebras that don't embed into each other affects the Wasserstein distance in other ways as well. Namely, it implies that the space of non-commutative laws with the Wasserstein distance is not separable. Okay, now if you're in classical probability theory, then this would be sound very horrible, because like in classical probability theory, you take measures on a compact set, right? Then of course you can have finitely supported measures will be dense in there, right? So it will definitely be separable, and they'll be dense in the weak star topology, and the weak star topology will be the same as the topology given by the Wasserstein distance, right? As long as you're on a compact set, right? And in a non-commutative setting, like none of these things are true. Okay, so one, it's not separable with respect to the Wasserstein distance. And this would also imply that it gives you a different topology than the weak star topology, because in the weak star topology, the space of non-commutative laws should be compact. And if it was compact and metrizable, then it would be forced to be separable with respect to that metric. So it can't be giving you the same topology. So how does this result work? Yeah, perhaps I don't know if I want to go into detail for the sake of time, but I'll try to go through this quickly, right? And the reason this works is basically because you can construct like uncountably many distinct things from some group with property T. So, and the property T will give you rigidity, and the rigidity will allow you to argue that the non-commutative laws you get out here will all be epsilon separated with respect to Wasserstein distance for some fixed epsilon. Right? And if you show that there's an uncountably many things that are separated by a fixed distance, then that will mean that the space is not separable. Right? And so how does this work? More specifically, you find there exists some property T group with uncountably many non-isomorphic quotients. And in fact, I don't even care if the quotients are not isomorphic. I mean, I just need to have there to be uncountably many distinct quotient maps. Okay, and so then you could take generators for the group G and then consider the images of the generators in each of these quotient groups. And then for each of these quotient groups, there's an associated von Neumann algebra, the group von Neumann algebra with the group trace, and you get some non-commutative random variables from that. And so then you have associated non-commutative laws. And then if you have a coupling of these non-commutative laws, then that will mean that there's copies of the different group von Neumann algebras inside some larger space, right? And there are copies of the group von Neumann algebras in there, and if you had them to be sufficiently close, then you would, if the images of the generators were sufficiently close, then you can use property T to argue that then the traces of all group elements in the two different representations would be uniformly close together. And the traces of them, since it's the group trace, will either be 0 or 1. So this forces the two like the image of each thing in the original group to be identity if and only if it's the identity in the other quotient map. So it forces the two quotient maps to be the same. Right. So that's the point. You use property T to argue this, and thus you deduce that these things have to be separated by some fixed distance. Right, so overall, it's not separable. Right? And another thing that fails is that you don't have finite dimensional approximation. Right? Assuming that this result of the negative solution to the Kahn embedding problem is valid, then that means another way to formulate the Kahn embedding problem is that whether all non-commutative laws of tuples in traceable von Neumann algebras could be weak star approximated by the ones that come from matrices. And assuming this paper is valid, then the answer is no, they cannot. There's some von Neumann algebras with a trace and some elements in there, and you cannot approximate their joint moments by matrices at all. And so then, based on this, you can argue that this affects the Wasserstein distance as well, meaning that there will be some tuples, in fact, tuples that come from finite dimensional matrix algebra, such that the optimal distance between them can only be realized in one of these non-Kahn embeddable von Neumann algebras, meaning von Neumann algebras that can't be approximated by matrices. So you can take tuples of matrices, and the only way to couple them optimally in the non-commutative setting cannot admit any finite dimensional approximation. And so this is very bad, right? Because you would think like maybe if you impose hypotheses on the two distributions that you input, then you would be able to obtain some kind of control over which algebra you do the optimal coupling in. But you cannot, right? You can take the nicest possible things imaginable, matrices, which actually probably are not that nice, and you need non-Kahn embeddable von Neumann algebra to optimally couple.
N is?
Well, I do not, because no one has like an explicit example of non-Kahn embeddable algebra, because it goes through this machinery of representing Turing machines through quantum games and then creating a quantum game that has certain properties, right? And then, but like I don't know if a human can adequately understand like how this like paradoxical computer program with halting gets encoded into some quantum game, right, and explicitly computed. Like maybe there's some computer-assisted way to get some handle on this, but we don't really have anything explicit.
The paper itself. Do you have doubts about the paper?
I mean, I think there are some people have doubts about it. I mean, to be honest, I'm relatively well convinced, but I don't know all the aspects of the paper. Right? It basically combines several different techniques, some which are in quantum information, and operator algebras, which Michael de la Salle has checked very carefully, and there's other ones that come from classical computing theory. And there was also like the initial version of the paper, they found some gap, which was like in some result that they were trying to cite and use. So then they updated the paper and they kind of like improved the result that they were trying to use so that it would actually do what they want. So it seems like I don't see anything particularly wrong with it, and the approach seems plausible. But I can't check it, and there are others who feel like because as operator algebraists we don't understand some of the techniques that we want a different way to prove it. And certainly it would be great to have explicit example of non-Kahn embeddable. Okay, So, right. So like I was saying, there's these pathologies in the non-commutative setting, right? It's not separable. You don't have finite dimensional approximations. And here's another way in which this fails. Well, okay, given the previous results, right? If the optimal coupling is in a non-coembedable thing, then there's no way to approximate it by finite dimensional things. And so arguing based on this, you can kind of take this example and perturb it into some nice random matrix model like the one that I had above, but for V which is not convex. And then in that case, it will be impossible for this to approach the non-commutative Wasserstein distance due to non-coembedability. Okay, but maybe that seems kind of cheap, because what if you just restricted to couplings that occurred in conembeddable von Neumann algebras? Then could you get this to work? And the answer to this is also no, in some sense, because there will be some kind of non-commutative tuples where even if you use the conembeddable Wasserstein distance, you cannot approximate this. This Wasserstein distance won't be the limit of the Wasserstein distance of any nice random matrix models like this. Meaning, if you had a random matrix model that had this nice potential V, then this random matrix model would have high entropy. It would have it would asymptotically realize the microstate free entropy of Voiculescu for these models. And basically, there's some kind of obstructions where, in certain cases, you can't make the matrix models have high enough entropy and also have small enough Wasserstein distance to do what you want. And the reason for this is ultimately basically that when you take random matrix models from some potential V, and the V is not necessarily convex, then it's not necessarily true that the marginals of this will have the same form. And this is really what breaks, because somehow, if you have the first couple x's and they're forced to commute with another one, and then you take the marginal distribution of the first one, then the random matrix model that you obtain as the marginal will have some sort of memory of the fact that there was something that approximately commuted with those things, even if that isn't clear, even if that can't be known just from the joint moments of that thing. Yes. Okay. So nonetheless, there are many things that are difficult or go wrong, but we still want to build an analog of optimal transport. And so the first observation along this lines was based on, was looking at the construction of Guillenet and Sliaktenko in 2014, where they constructed this kind of gradient of convex function, which does the transport of something into the semicirculars. And there was still a question of whether this thing was optimal, in the sense, does this actually realize the non-commutative Wasserstein distance, right? And given what I said before about non-coembedable von Neumann algebras existing, right? How do we know that there isn't magically some way to make the distance even smaller by using some kind of forbidden non-coembedable von Neumann algebra? So you need to do something. You need some tool to make this work. And the insight is to use the Monge-Kantorovich duality and the related notion of Legendre transform of convex function, which I won't explain what that is. But we started out by realizing that you can construct such a thing and use it to verify that this is actually optimal, right? So to know that it's optimal, you need to you want to express the distance in terms of some kind of test functions that are nice. That's the idea. And this is the Monge-Kantorovich duality that was mentioned in the pre-seminar. And so then we developed a non-commutative analog of this, and the goal, is again to characterize the optimal coupling and to characterize the Wasserstein distance in terms of some kind of test function, right? So here we'll have some functions f and g that are convex, and here I represent this as the dual pairing, which is integrating a function against a measure. But here for the non-commutative law, it would just be, pairing that non-commutative law with that function. And So the Monte-Kontorovich duality has a couple of different statements to it, but one thing is that the maximal inner product is realized by the infimum of something else, right? So the supremum of one thing is the infimum of something else, and the infimum of something here where you have just functions of x and a function of y that are separate. But you optimize over all pairs of functions that satisfy such an inequality here. And so if this function satisfies such an inequality, then it will be clear just from this that whatever is the value of the function, paired with that non-commutative law, it always has to be greater than or equal to the inner product of the things in the coupling. Right? And so there's one direction of this inequality which is clear, and the other one that you have to work to prove, like you have to build the correct f and g that will do this. And furthermore, as in the classical theory, you want to say that the optimal coupling occurs when y is the gradient of some convex function applied to x. And then in the general setting, the function is not necessarily differentiable, but you have like a subgradient, like a vector that defines a supporting hyperplane to the graph of the convex function. So the point is that the optimal couplings can be characterized in this way. And I guess the reason the maximal inner product is relevant is because if your x and y are fixed in distribution and you want to minimize the distance, that's the same as maximizing the inner product. So we have some kind of version of this. And for the sake of time, I mean, if you want to know the details of what the statement actually is, you can ask me later, right? But how did we define the functions? We tried to define some analog of convex functions. And what do we want? We have a function which is a function that you can evaluate on any tracial von Neumann algebra. So if you want, it's really like a tuple of functions, like there's one version of the function for each von Neumann algebra. And you want some kind of consistency condition that if you embed one into von Neumann algebra into another one in a trace preserving way, then the value of the functions will be the same. If you evaluate it on if you evaluate it on the image of the x versus on the x itself. And then we have this E-convexity condition, and in addition to wanting each function itself to be convex and lower semi-continuous, then you want the corresponding this inequality, that if you have an embedding, and then if you take the conditional expectation that goes in the reverse direction, there's a unique trace preserving conditional expectation in the von Neumann setting, then the value of f on the conditional expectation of x is less than or equal to the value of f on x. And you should think of this like Jensen's inequality. Jensen's inequality says that the expectation of a convex function is greater than or equal to the convex function of the expectation. Right? And this is one condition that we want in the definition. Right? So we had defined these E-convex functions in this way, and these functions can be used in this duality. But maybe there's and even if this definition with conditional expectation seems kind of weird or artificial, I mean, another way to think of it is that the E-convexity means that not only does the function have a subgradient vector or a supporting hyperplane at each point, but the gradient vector used for this can be chosen from the von Neumann algebra generated by the point x where you're evaluating the function. And that, I mean, is pretty natural. And so it's easy to check that if you had like non-commutative polynomials or some other thing that was smooth, and if it was convex, then it would satisfy this E-convexity, because in that case it's clear that the gradient is some non-commutative polynomial applied to the x, so it's in the von Neumann algebra. So, but the difficulty with this theorem, or maybe the limitation of the theorem, is that it's definitely not true that all these convex functions can be approximated by ones that are smooth or that actually come from polynomials, right? And so sort of the contrast between weak-star topology and Wasserstein topology applies also to the functions, right? The functions that you get here will not all be weak-star continuous, and this is also kind of bad because in random matrix theory you have the laws converging in weak-star topology, so if you have a function that's not continuous on weak star topology, it's hard to use it and apply it to the random matrix models, right? So, yeah. But nonetheless, this theorem still gives you some nice application, at least a little bit, which is that, that if you take the x and y, and if they're optimally coupled, and then if you take the convex interpolation between x and y, then anything that's strictly in the interior, it will generate the entire von Neumann algebra generated by x and y, right? And the reason for this is basically like you take the convex functions and you create the convex functions that would witness the duality for the things in the middle, and then those convex functions will be differentiable. And so you'll be able to say that you actually have a gradient and that it's in the von Neumann algebra, and so you get that the von Neumann algebras are the same. Okay, so I think at this point I'm out of time. I do have more to say about automorphism orbits, which if you want, I mean, if you ask me this as a question, then I can say more about this, but I think I'll stop now in case anyone wants to leave.
Thanks very much, David, for a nice talk. Are there any questions, locally or online? I have a question. So this very last theorem, is there a classical analog of this that I should think about?
Yeah, this is true in the classical case. So in the classical, well, yeah, I mean, you just have commutative von Neumann algebras, right? But maybe in terms of measure theory, you might think like the sigma algebra generated by this random variable of 1 minus tx plus ty. The sigma algebra generated by this is the same as the sigma algebra generated by x and y jointly, right? And you could think of the example of point masses. So you can consider like 3 point masses of weight 1/3 versus 2 point masses of weight 1/2, right? And in that case, there's no way to, when you take the optimal coupling, wait, maybe we'll write on here. You know, say you have 3 points versus 2 versus 2 points, right? And then the optimal coupling would be basically something like this, right? And let's say you have 1/3 on each of these and 1/2 on each of these. And in the optimal coupling, you would match up the mass somehow, right? You would take 1/3 of mass that's shared between these and 1/6 that's shared between the middle one here with each of those two. Right? And in that case, and so then the probability space where the coupling generated by these two random variables would be a probability space with 4 points, which have a weight of 1/3, 1/6, 1/6, and 1/3. And if you take, and the x, you know, and the random variables x and y would be, you know, the evaluations of these things here. And if you take the linear combination of x and y that's strictly in between, then it will obtain different values on all 4 of the different points, and so it will generate the whole thing, right? So even if the optimal coupling isn't obtained by a transport function, it's still true that if you interpolate in between, then it does generate the entire sigma algebra.
Oh, yeah.
You mentioned that Ozawa constructed the noun isomorphic group von Neumann algebra by.
Yeah. Yeah, so let me see, where is this here? Right, so it's really this having uncountably many distinct quotients property, right? That they use the, yeah, so somehow like the ideas, like the geometric group theory is used to construct these things. Yeah, and the fact that you have property T, it's not necessary, it's not part of the proof of like how you construct the group with these uncountably many different quotients. The property T is just an additional property that I want to use in order to apply that, and also which Ozawa used. but you can also arrange that because there's many hyperbolic property T groups. I really like the ideas of Gromov, which Olshansky used to give a rigorous proof of this, that's where the geometric group theory comes in, like how to construct, that under certain conditions it will have, all these different quotients. But I guess maybe I can't, I'm not an expert in that, so I can't say that much more here, but yeah.
Anything else? I mean, I would like to hear about the automorphism orbits, but maybe we talk tomorrow, whoever's interested. So then let's thank David again. I think the next talk is on February 18th. Is that right? By Andrea Chiandra? No. Someone from Norway. Oh, there we go. Matthias Palmström. So hope to see you then.